So welcome back to the class on electrical machines 2. In this lecture, we are going to discuss about the circle diagram of three-phase induction machine. Three-phase induction machine that becomes a motor as well as a generator. So why we are calling the circle diagram? If you find the locus of stator current of induction motor by varying the load on induction motor, then it becomes a off circuit. The same manner, if you find the locus of induction generator by varying the load on an induction generator, it gives the remaining off cycle. Off cycle for the induction motor, off cycle for the induction generator. If we combine this one, it gives the circle diagram for the induction. From the circle diagram also we can find out the performance parameters of induction motor as well as induction generator. But here in this class we are going to discuss about the how do you calculate the performance parameters of an induction motor volume. From the equivalent circuit of induction motor also we can calculate the performance parameters of induction motor. This is one more graphical method by which also we can calculate the performance parameters of induction motor. Now we are going to see one by one. Circle diagram for induction motor. It is a graphical method of calculation. Circle diagram is used to calculate the performance parameters of induction motor. The performance parameters are the efficiency, losses in a motor, constant losses or the fixed losses, torque, speed at any value of the load. That will be a full load or the off load. But here to develop the circle diagram for the induction motor, we have to conduct some test on an induction motor, that is a no load test and block rotor. Already we studied how to conduct a no load test and block rotor test in induction motor. From the data, we are going to develop the circle diagram for the induction motor. From the no load test, let us take V1 on the vertical axis, where V1 is nothing but a per phase voltage applied to the induction motor during the no load. Cos of theta naught is nothing but a no load power factor of induction motor, that is equal to PNL by VNL into INL. These three are nothing but readings in a no load test of an induction motor. Moreover, the PNL, INL, VNL are the per phase power current voltage during the no load test. Suppose if these values we got for the three phase, then we have to convert it into the per phase value. When you come to the current and voltage, that is highly depending upon the whether the stator winding is connected with star or delta. So depending upon the connection which is given in the numerical, that you have to convert it into the per phase values. Those per phase values have to take here, then you have to find out the no load power factor of induction. INL is nothing but a no load per phase current taken by the induction motor during the no load test. From a block rotor test, already we know that in a block rotor test, we are applying the fractional voltage to the induction motor. All these parameters, whatever the parameters we are getting from the block rotor test, converting to the rated voltage. A short circuit current at a rated value of voltage, that is ISC equal to IBR into V1 by VBR, where ISC is nothing but a short circuit current if you apply the full voltage to the induction motor. This current is also nothing but a per phase current. IBR is nothing but a during the block rotor test, how much current is taken by the induction motor. V1 is nothing but a per phase rated voltage. VBR is nothing but a per phase block rotor voltage. The same manner, short circuit power at a rated value of voltage, that is denoted by P suffix SC, that is equal to PBR into V1 by VBR whole square. The PBR is nothing but the per phase power taken by the induction motor during the block rotor. V1 is nothing but a per phase rated voltage. VBR is nothing but a per phase voltage applied to the induction motor during the block rotor. Now, the power factor of induction motor during the block rotor test, cos of theta BR equal to PBR by VBR IBR equal to VBC by V1 IC. These values are nothing but what we got from the block rotor test. These values are nothing but at rated voltage. So any values you can take it to calculate the power factor of induction motor during the block rotor test, we are getting same value. Now take the scale such a way that the short circuit current, nothing but this current, is minimum 20 centimeters for getting the accurate values. Now we have a no load power factor of induction motor, no load current, and short circuit current taken by the induction motor if you apply the rated voltage, and a power factor of induction motor during the short circuit. Now we want to represent these quantities in a graph, so we have to take the scale. How do you take a scale means the short circuit current will be taken the 20 centimeters for getting accurate values. Suppose if you are getting the IS is 100 amperes. Now you take the 5 amperes is 1 centimeter. Then you are getting the total current will be representing the 20 centimeters. In that manner, you have to take the scale for the current. The same manner, you have to convert the no load current taken by the induction motor into the centimeters also by using the same scale. Now we are going to see how to draw the circle diagram. First, we have taken the x-axis, and the y-axis we have taken the voltage, which is applied to the induction motor. First, you have to represent the no load current. Already you have taken the current scale, so you have to take the no load current. Now you have to convert this no load current into the centimeters. This is the no load power factor. So from the y-axis, you have to measure the no load power factor. Now from this point, you have to draw how much length no load current is you have taken. This is the no load current. Now you have to draw the one horizontal line from the tip of the I0 and parallel to the x-axis. Next, you have to represent the short circuit current taken by the induction motor if you apply the rated voltage. Now this angle already we calculated. This length equal to, already we have taken the current scale. How much length we are getting, the same amount of the length you have to draw the line. That is representing the OA. This is O. This no load current is nothing but O dash. This is the short circuit current, that is OA. Now we combine the A and O dash, that is representing the output line. We are using the bisection method to bisect the O dash A. This is output line. To combine these two bisecting arcs, this dotted line is intersecting this black line at this point. That point you take as a C. Now C is representing the center for the circle. Now take the C is the center and length O dash C is a radius and draw a arc. This is arc, half circle. This half circle is passing from the O dash A and also touching this black horizontal line at a point D. Now I have to draw one vertical line from the A perpendicular to the x-axis. The length of this vector is representing how much power is taken by the induction motor during the blocked rotor test if we apply the rated voltage. See here, you observe this one. AE, EF and FG. Length FG is representing the constant losses occurs in induction motor. Now the remaining length you have to divide. How we are going to divide means that is depending upon how much stator copper loss and rotor copper loss will occur in an induction motor. Because during the blocked rotor test, how much power is taken by the induction motor, the total power will be wasted as a stator copper loss, rotor copper loss, stator core loss, and windage and friction loss. Now the length AE by EF, FG is nothing but a fixed losses. AF length you have to divide. AE by EF equal to rotor copper loss by stator copper loss. Suppose if you know the rotor copper loss and stator copper loss, then we can divide this. Generally, we are taking the rotor copper loss and stator copper loss equal. So we have to divide this length equally. That point is nothing but E. So from the point E, you have to draw one line by combining the O dash. This line is nothing but a torque line. Now we want to find out at a full load, how much is the loss occurs in induction motor and how much is the current taken by the induction. Now up to here, we know the current scale voltage. Now we are going to take the power scale because nameplate detail of induction motor itself, it is given the power. Now that power you can able to convert it into the centimeters. Then only you can represent in a circle diagram. Now we are finding the power scale. Already we have taken the X. X is nothing but a per phase current scale, amperes per centimeter. V1 is nothing but a per phase rated voltage. Power scale equal to X into V1, that is equal to watts by centimeters. So here we know the rated power. The full load power divided by the power scale that gives the rated power in a centimeter. Once we got this length, then you have to draw that length from A, extension of this line. Extension of this line. Length is representing the full load output power. Now from B, I have to draw one dotted line parallel to the output line by means of a scale. This is the black dotted line. That is intersecting the half circle at this point. So from this point to origin, I will draw one vector That is, this vector is representing the current taken by the induction motor at a full load. Now from this point you drive one vertical line perpendicular to the x-axis. Now you take this point as a P. Now give the labeling. This is nothing but a phi L. Phi L is nothing but a angle between the voltage to the full load current. OA is nothing but a full load current. Now this point is nothing but Q. This point is nothing but R. This point is nothing but a S. This point is nothing but a T. Now from this diagram, now we are going to find out some of the parameters of induction motor at a full load. This PQ is nothing but a rotor output power at a full load. QR is nothing but a rotor copper loss at a full load. Length RS is nothing but a stator copper loss at a full load. The length ST is nothing but constant loss. We can find the slip of the induction motor at full load. The slip of the induction motor at full load equal to rotor copper loss by rotor input. The rotor copper loss is representing the length QR and rotor input is representing the length PR. Take the ratio between these two, we are getting the slip of the induction motor at a full load. Now the total losses is representing the length QT. The efficiency of induction motor equal to length PQ by length PT into 100. That gives the efficiency of a induction motor at a full load. Next, full load power factor. Already we know the angle between the V1 and P, that is pi L. Cos of this angle is nothing but a full load power factor. Input current taken by the induction motor at a full load, that is equal to length OP. So whatever the lengths we got it here, so if that quantity is a current, then you have to use the current scale, then convert it into the amperes. Suppose if that quantity is a power, then use the power scale, then you have to convert it to that quantity into the power. In that manner, you are getting the actual values of induction motor at any value of the load. Thank you very much. If you have any doubt, you can ask me directly or you can ask in the comment box of my YouTube channel, so that I'm always welcome to answer all your questions.